Hello, welcome to this video lesson on elimination reactions, the other type of reaction mechanism that we deal with in year 12 of the chemistry A level. So elimination reactions, what are they? Well, as the name suggests, a small group of atoms or an atom is eliminated from a larger atom and not replaced, like it is in a substitution reaction. The bit that breaks off the molecule is replaced by something else in a substitution reaction. Not so in elimination reactions. It breaks off and leaves, and the rest of the molecule forms new bonds with itself and becomes a new molecule. So that's elimination reactions, and we're going to study the reaction mechanism and also the conditions under which we can make a reaction use the elimination mechanism. So when we want to use the elimination reaction mechanism, because we want a certain product from a halogenic alkane, and by the way, we're still dealing with halogenic alkanes as the reactant. When we want to produce a certain molecule that we would achieve with an elimination reaction mechanism, we're going to use reflux. And so the reflux kit looks like this. And so with my red pen, I'm just going to highlight the reaction vessel here. So this is a water bath, this bit that I'm sketching around. So that's providing the heat. And then the reaction mixture is in here. And that has been heated, and these components are volatile, and the halogenic alkanes have got reasonably low boiling points, and so they're going to vaporize and would normally escape, except we have a cooling jacket here. So this item here you'll recognize as a cooling jacket, and we'd have cold water in here and water out at the top. And then what would happen would be that the vapor would condense and drip back into the reaction vessel and mixture to continue to react, to have another chance to react. And to prevent pressure building up too much, the top of the condensing column is in this case filled with cotton wool, so that we can let any excess pressure be relieved. So that's the kit that we use to do a reflux reaction. Now we can do reflux and make a substitution reaction, or we can do reflux and make a elimination reaction mechanism. So if we want to do elimination, then we're going to have our other reactant, right? So we're going to use the hydroxide ion again as the reactant. So the first reaction is the halogenic alkane, of course, halogenic alkane, and we're going to add that to hydroxide ion. Now I've not called it a nucleophile this time, and I've done that deliberately. Actually, in the case of elimination, it's going to act as a base. We're going to come back to that in a second. But what we would do in under reflux is we would react these in ethanol, right? So we would dissolve the hydroxide ion in ethanol. All right, so the hydroxide ion would be dissolved in ethanol. It would be reacted with the halogenic alkane, and in that case, it would react under an elimination mechanism to create a certain product. Now we can also use reflux to create a substitution reaction, and which one it is determined by the conditions. Right? So again, we've got a halogenic alkane. Again, we've got hydroxide ion, and in this case it is the nucleophile. But this time it's dissolved in water. Okay, so depending on the solvent, if the solvent's water, you get a substitution reaction. If the solvent's ethanol, you get an elimination reaction. Okay, so that's reflux, and most of these reactions are take place under reflux. And what we're going to have a look at now is the elimination reaction mechanism. So in order to study the elimination reaction mechanism, we're going to look at an example. We're going to take 2-bromopropane, which is our halogenoalkane. So 2-bromopropane is CH3 CHBr CH3. We're going to react that with potassium hydroxide. That's to provide our hydroxide ions. And of course, we're going to do this under reflux with the hydroxide dissolved in ethanol. So let's put reflux and ethanol as our conditions. And then we're actually going to get an alkene. CH2CH3 propene. And we're going to get a water molecule. And we're going to get some potassium bromide. So this time we're going to get a different product with the elimination mechanism. We're going to get an alkene, propene, and this is how it actually works. This is what the mechanism is, step by step. So to start with, let's draw the displayed formula of our 2-bromopropane. So propane's got 3 carbons, 1, 2, 3. It's 2-bromo, so the bromine is on number 2 carbon. Let's draw our hydrogens in. There's our halogenoalkane, like so. Let's draw our hydroxide ion in here with, again, our lone pair. And we're reacting those two together under reflux with ethanol. And when we do so, what happens? Well, the first thing that happens is our hydroxide ion acts as a base. And actually in year 13, when we do acids and bases in more detail, you learn that the definition of a base is a proton acceptor. The proton, I'm just going to circle it in red here. The proton that we're talking about is going to be this hydrogen atom here that is a proton because it leaves its electron behind. Right, so let's go back to dark blue, and we can see that this lone pair is going to attack that hydrogen. And it's not acting as a nucleophile, it's acting as a base. I really want to make that clear. So it's going to take that hydrogen, and when it does so, the hydrogen atom is going to leave without its electron that it's left in this bond, and both of the electrons in this bond are going to have to find their way over to here. And that's going to form a double bond with the middle carbon. But before we draw the product out, let's just remind ourselves that this bromine here is going to be delta minus, and this carbon here is going to be delta positive. So let's draw what we've done so far on the product side. We've got carbon, hydrogen. It's lost its top hydrogen. Still got the 2 other carbons, but it has formed a double bond with the adjacent carbon there. And I've got the middle carbon still bonded to the bromine, and this doesn't exist for very long, sort of simultaneously does something else. And then we've got the CH3 group on the other side. So you can see this is not a stable atom. We're going to fix it in a second. But I want to just track those electrons. So I'm going to the electrons that were in this carbon-hydrogen bond on the left, you see I'm drawing them in red there, they have made their way over to this bond here. They've made that bond there. And this hydrogen that I'll change to green, and I'm going to draw over the hydrogen that was attacked by the hydroxide ion. And that hydrogen makes its way and bonds with the hydroxide ion that I've drawn in dark blue there to make a water molecule. So that's the steps that we've done so far. But of course, this middle carbon now has 5 bonds. That can't be a permanent situation. And what's more, bromine likes electrons. So we're just going to put our delta negatives in there. So what happens is these electrons that are in the carbon-bromine bond say, okay, I'm going to have a much better time with the bromine, and so they go onto the bromine, and the bromine leaves as an ion because it's got that extra pair of electrons there. So let's draw down here what the product is. So the left-hand carbon has still got 2 hydrogens on it. Let's draw them a bit spaced out now. The double bond is still there. The top hydrogen is still there, but the bromine on the bottom has gone now. And we have the methyl group on the right-hand side is still there. Okay, so let's just track our electrons. We've got bromine leaving, bromine ion leaving with its lone pair. Okay, so that's what we get. Let's just track the electrons. What colour should we use? Let's go to purple for this this pair of electrons. So in purple, on the intermediary molecule, I'm drawing 2 electrons in there in that carbon-bromine bond, and they become these electrons that I'm overdrawing here on the bromide ion. So that's where they've gone, and then you get the alkene that's left, which I'm denoting there, and we've got a bromide ion that's left, and we get a water molecule that's left. And so they're the 3 products that are formed in the reaction mechanism. So we've got 3 curly arrows to take note of in an elimination reaction mechanism, whereas I think before we had 2 curly arrows. So now we've got 3 curly arrows. If we remember that, we'll probably remember the mechanism. Okay, so that's an example of the reaction mechanism there. Usually when you're writing it in an exam, you would put your 3 curly arrows on the one molecule, which I'll show you an example of in a minute. So if you did that, you would actually go straight from this step here to the final molecule, like so. So now we're going to have a look at what's called concurrent substitution and elimination. And that is just starting from the same halogen alkane. We can use reflux with a water solvent and have a substitution mechanism. Or we can use reflux in ethanol and have an elimination mechanism. So let's start with the same halogen alkane. Let's use bromoethane again. Let's draw that out. So here's bromoethane. Bear with me while I draw it all out. And that's the molecule we're going to use under reflux and water. And let's draw the same molecule out again so that we can see that from the same halogen alkane, because we use different reaction conditions, then we can make a different product. Okay, so we've got bromoethane in both cases, but in this case we're going to have hydroxide ions dissolved in water under reflux conditions, whereas in this one we're going to have hydroxide ions dissolved in ethanol, also reflux. And so the top one is going to be substitution, the bottom one is going to be elimination. But what I want to make quite sure that you know this is that this hydroxide ion is in the substitution mechanism is a nucleophile, whereas the hydroxide ion in the elimination mechanism is acting as a base, i.e. a proton acceptor. Okay, so let's do the reaction mechanism for substitution first. And let's start by putting our partial charges on there. So we're going to have delta negative bromide and a bromine and a delta positive carbon. So let's draw our nucleophile in. Our nucleophile is our hydroxide ion with its lone pair, and that lone pair is going to attack the carbon atom with those two electrons in the lone pair forming a new covalent bond, making that carbon atom unstable with 5 bonds. So then the electrons that are in that carbon bromine bond make their way over onto the bromine atom, making a bromide ion, which then leaves. Okay, so after those two steps we get carbon with 3 hydrogens, like so, and the other carbon is bonded to our hydroxyl group now. Still got its 2 hydrogens, and the bromide has left. For completeness, let's give it its lone pair. So they're the 2 products we get. So this is ethanol. This is ethanol, and that's the substitution mechanism at the top because we had water as a solvent. Okay, so moving down to the bottom, we're starting with hydroxide ions and bromoethane again, but this time we've got ethanol as the solvent. We're going to reflux that, and because we've got ethanol as the solvent, we're going to get elimination. So in the same way, let's put our charges in, like so. Let's then put our hydroxide ion in with its lone pair. And that hydroxide ion, acting as a base being a proton acceptor, remember, is going to attack a hydrogen atom. Now, I've chosen this hydrogen atom deliberately. I could have chosen any of the hydrogen atoms on the methyl group. I could have chosen this one and this one as well, but I wouldn't choose the alpha carbon. I wouldn't choose the carbon that's bonded to the bromine. The reaction mechanism wouldn't work that way. So it's going to attack that hydrogen and accept it as a proton. So the hydrogen leaves without its electron, i.e. it leaves as a proton. And so the electrons that are in that bond, they have to go somewhere, and they go to the carbon-carbon, forming a double bond there. Now the alpha carbon, that's the carbon attached to the bromine, is unstable because it's got 5 bonds, and so the bond between the carbon and the bromine breaks because the electrons make their way wholly onto the bromine atom, making a bromide ion. So there's our 3 curly arrows for elimination, and what we're left with is a carbon with now 2 hydrogens on it, because one of them has been ripped off by the hydroxide base, but we've got a double bond in between our 2 carbons, and the bromine is gone, and so the carbon is left bonded to 2 hydrogen atoms, and as before, the bromine leaves, but in this case, I think that last slide cut off a little bit prematurely, but we were virtually finished there. I just needed to also say that the water molecule would be produced as well as one of the products, that being the combination of the hydroxide ion acting as a base and the proton that was ripped off from the bromoalkane. So hopefully that's been clear, not only the elimination reaction mechanism, but also how you can get concurrent substitution and elimination when you, depending on what solvent you use in your reflux. And in fact, if you used a mixture of solvents, i.e. a mixture of ethanol and water, you would get a mixture of the different products of the alkene and the alcohol. So hopefully that's been clear.